So we're going to look at the trig identities, or more correctly, what we call the Pythagorean trig identities. And the reason they're called the Pythagorean trig identities, here's our unit circle. If I was to draw in the first quadrant right-angled triangle, and as it's a unit circle, we know the hypotenuse is 1. The x value I could find, and the y value I could find, but we know that the points on the circle, x squared plus y squared equals 1. Now the y value, well, y over 1 would be the sine of theta, and the x value, well, x over 1 would be the cosine of theta. As I say, we know it lies on the circle, x squared plus y squared equals 1, so we end up with sine squared plus cos squared equals 1. So that's why it's called the Pythagorean trig identity, because it comes from Pythagoras' theorem. So that rule will always be true no matter what the size of the angle is. Sine squared plus cos squared is equal to 1. But then we can play around with it. I'm going to divide everything by sine squared. So if I divide sine squared by sine squared, that's going to be 1. Cos squared plus sine squared, well, sine on cos we know is tan, so it must be the reciprocal of tan. And the reciprocal of sine is cosec. So we get a second identity that we can use. 1 plus cot squared is equal to cosec squared. Well, what if I divided by cos theta instead? Sine on cos, well, we know that's tan. Cos on cos is 1, of course, and then the reciprocal of cos is sec. So we get tan squared plus 1 is sec squared. So they are the 3 Pythagorean trig identities. They are in fact all the same. They all come from the sine squared plus cos squared is equal to 1. But using those we can solve all sorts of problems. In addition, with this ratio, it's not a Pythagorean trig identity, but it certainly comes in useful when solving some of these problems, is remembering that tan theta can be rewritten as sine on cos. I start with this question because I don't know why they always seem to use this sort of question when you're doing trig identities. And personally, I wouldn't use trig identities to do it. I think what they want you to do is say, well, I know what cos theta is, so I could sub it into sine squared plus cos squared equals 1, and then I could go and find sine theta. Personally, though, if I see something like this, I prefer to draw a triangle that told me cos theta is 3/4, and so therefore the other side will be root 7, and I can just read off the triangle what the sine of theta is. Now, they've given me additional information. Tan theta is negative. So cos theta was 3/4, tan theta is negative, so I must be in which quadrant? And in the 4th quadrant, sine is negative. So I'll read off my triangle, but it'll be negative root 7 on 4. I personally think that's quicker than using the trig identity. These are the sorts of things we use the trig identities for, simplifying down terms. Now I'll start with, well, one like this, 1 minus cos squared, is something where normally we just write the answer down. But let's just pretend that, oh, okay, I've got no idea how to do this. Well, I've got a little idea. I know what the trig identities are. So 1 minus cos squared, well, hang on, I've got a trig relationship that says sine squared plus cos squared is equal to 1. So theoretically, I could substitute in for cos squared 1 minus sine squared, and then I get 1 minus 1 plus sine squared. Oh, it's just sine squared. Now, in reality, I would hope you'll end up looking at 1 minus cos squared and you just know, oh, that's sine squared. But what I'm getting at with this, whenever we're playing with the trig identities, if you're unsure what to do, substitute in for the square term. Because the beautiful thing about the trig identities is they all involve different ratios, so you can't substitute in the wrong one. So if I had sec squared minus tan squared, again, that's one that you could possibly look at and just have the answer straight away. But let's say we didn't. Sec squared, tan squared. I've got the trig identity, 1 plus tan squared is sec squared. So I think it probably makes more sense to substitute in for the sec squared, as it's already rearranged nicely for me. So I get 1 plus tan squared minus tan squared. Oh, that one's 1. Tan theta, cos theta. All right, obviously I'm not going to use one of my trig identities because there's no square there. So perhaps I'm going to use that other relationship, that tan theta is sine on cos. Well, sine on cos, the cosines will cancel. I'm left with sine. They're the sorts of things you're looking for. So when they now ask me to prove something like this, 2 sec squared alpha minus 2 over 4 tan alpha is tan alpha on 2. The first thing I want to point out is don't skip steps. Because when they've given you the answer, it's very easy to fudge a question because you know what the answer has to be. So whoever's marking a solution will want to know, did they really know what they were doing, or did they just fudge it because they knew what the answer was? So when we do it, we put all our steps in. It doesn't matter. You can start with the left-hand side, you can start with the right-hand side. It's up to you. I'm going to start with the left-hand side because that's the one that's got the square in it. Sec squared, okay, I know that's 1 plus tan squared. So I substitute in. Let's tidy the top up. I get 2 plus 2 tan squared minus 2. Okay, well 2 minus 2 disappears. And now that cancels quite nicely, doesn't it? We've got the 2 goes into the 4, the tan goes into the tan squared. I get the tan alpha on 2. So the first step, you always write down the side you're starting with. In this case, I started with the left-hand side, and then work your way down, and hopefully you'll end up with the right-hand side. Of course, the other ways you could do it, I say you didn't have to start with the left-hand side. I could have started with the right-hand side and then worked my way down to show the left-hand side. Sometimes you get stuck, and so you work on them independently. So you might start with the left-hand side and you come up with an expression and you go, oh, gee, I don't really know where to go from there. So now I'll go work on the right-hand side, and you come down and you go, oh, hang on a sec. I've been able to show it's the same expression. And once I've showed the two things are equal to the same thing, they've got to be equal. But what you never do is you never solve it like an equation. Because it's not an equation to solve. It's not like I'm saying, find what alpha is equal to. You shouldn't be able to find what alpha is equal to, because these are always equal regardless of the value of alpha. It's an identity. So you can't actually find the value of alpha because everything will be able to substitute in. Well, as long as it's in the domain, of course. And, ooh. So the other way I could have done it is I could have started with the right-hand side. So tan alpha on 2. Personally, I don't think it's a great way to go, but how would I have done it? Well, tan alpha on 2, I need a trig identity. Now, because they've given me a proof, I know where I need to head to. So that's what gave me the idea in this one is, well, I got to get tan alpha on the bottom of the fraction. So that's why I said, well, okay, let's multiply top and bottom by tan. It gets the tan alpha on the bottom that I want, and it turns the top into tan squared, so now I can use a trig identity. Tan squared would be sec squared minus 1, and if I multiply top and bottom by 2, I get the result. So as I say, my gut feeling is I wouldn't have gone that way. Reality is it's probably a bit quicker, this one, than starting with the left-hand side. It only took me a few steps. It doesn't matter. It's totally up to you, how you approach it. Another idea, because sometimes it's a lot easier to show something's 0. So you move it to the left-hand side. Now, I just said don't solve it like an equation. And you might be thinking, well, hang on, you're solving it like an equation. No, what I'm doing is I'm changing what it is I'm trying to prove. So that's okay. I can move that and then say, now this is what I want to prove. From that point on, I don't treat it like an equation. But if I can end up proving that this is equal to 0, once it becomes a fact, then I can move things. All right, so the left-hand side now just becomes 2 sec squared alpha minus 2 on 4 tan alpha minus tan alpha on 2. Well, let's create one fraction. Common denominator would be 4 tan alpha. So my top is now 2 sec squared minus 2 tan squared. But we know that sec squared is 1 plus tan squared. And that's going to equal 0. All the top cancels, and I've got 0. So now I can say, well, hang on. That means I know what I'm trying to prove is true. So therefore, I could move that tan alpha on 2 to the other side. It's also now got to be true. That's an alternative way of doing trig identities. As I say, up to you how you end up approaching it. Okay.